Hey, good morning, everybody. This is the last lesson on natural selection, on evolution, Darwin's work. So let's get started. Okay, so at this point here, Darwin's kind of developed his theories. He has his ideas, his thought process, his thesis, his hypothesis on natural selection. But now it's time for him to kind of put it together and publish it. So he traveled around the world on the HMS Beagle. He saw these different organisms, right? Tons of different specimens, observations. He developed his theories, which we've spoke about, the concept of natural selection, right? Survival of the fittest. And when it came time to really publish his work, it was really against the thinking of the time, right? The thinking of the time, the Church of England was very powerful, and there are definitely a lot of creationist views, right? That the Church God created all these different organisms and created them in whatever likeness that they are. So a horse was created to be a horse, right? A fly was created to be a fly. Humans were created to be humans, and they were directly created by God. And with that, there was also kind of a timeline issue at this point. Like, people at this time really thought the Earth was about 5,000 to 6,000 years old. All right, so those are two major ideas that are popular in society that Darwin's work is really going to contradict. So he took a lot of thought, and he was very nervous in publishing his work. And if you just even think about it, but let's just take the time aspect, right? Natural selection, if we all come from a common ancestor, in order for that to be possible, you can't do it in just 5,000 to 6,000 years, right? You need millions, billions of years in order for that to take place. Okay, so it's kind of like where we stand at this point when Darwin's going to get ready to publish his theory, and that's kind of like the thought process that really kind of permeates society, with the Church of England and in England and Europe of the time. Okay. So Darwin really needed to kind of look to other scientists and the work of other scientists to help kind of support or help Darwin with his work. And one scientist he looked at was Charles Lyell. Charles Lyell didn't work with. There's another geologist named Hutton as well, but we'll just kind of deal with Lyell. And he was a geologist, which means he studies rocks. And with studying rocks, he studies things like erosion, sedimentation, right? And studies like the slow processes that can change our Earth over long periods of time. So he kind of studied these geological forces that shape the face of the Earth. And with that, he started kind of extrapolating, going, listen, if we're looking at erosion or sedimentation, right, this amount of erosion, this amount of sedimentation can't happen in just 5,000 to 6,000 years, right? The Earth must be much older. And here's kind of a great example. So if you haven't figured out yet, this is the Grand Canyon. And what's the name of the river that runs through the Grand Canyon? Give you a second. Hopefully you said the Colorado River. And you can definitely see how the Colorado River was, helped to shape the Grand Canyon. Like, look, this river kind of running through. You can see the erosion, right, in the shaping of that Grand Canyon, partially from the Colorado River. If you kind of look at the rate of erosion, this didn't just take a few hundred years, right? This took thousands and thousands, if not millions of years to form, right? So kind of looking at erosion, looking at rates of erosion, right? We really extrapolated that the Earth is, definitely far older than 5,000 to 6,000 years. Now, Lyell was probably about 1 million years old, is kind of what his thought process was. A little bit off. The Earth's about 4.5 billion years old, but 1 million years compared to people thinking that the Earth is only 5,000 years old, 1 million years is like an infinite number, right? It doesn't matter. It's old enough that they can't really process how old 1 million years really is. All right, so Darwin helped you kind of use this information to help kind of, bolster his theory of natural selection. Now he has a time frame for it to happen. The other thing was, when Darwin was kind of looking at fossils, like, he was seeing fossils that were so old that he didn't really have a context to say, well, when did these fossils exist? Because the Earth was only 5,000 to 6,000 years old, people believed at that time. So it all kind of helps Darwin with his theories. Okay. Another person that really Darwin leaned on wasn't a scientist. He was an economist. His name was Thomas Malthus. And Malthus really studied humans, and he studied kind of growth rates, right? Economy and growth rates in human populations. And with that, he kind of looked and said, hey, you know what? if the birth rate is higher than the death rate in humans, right? So there's going to be more babies than there are people who are dying, right? Your population is going to grow exponentially. Well, why isn't the world just flooded with humans? Why haven't we completely encompassed the entire world? Right? And his theory was, well, there are pressures that kind of keep it in check, right? There's limitations of resources. There's war, famine, right? Not enough food, limitations of resources, disease, right? All these are kind of limiting factors that kind of limited the growth of the human population. And Malthus would look like, oh, well, which humans are going to survive? Which countries are going to survive? And he kind of had the idea is, well, the strongest countries are going to survive. Like the first world countries are the ones that are going to be able to gain those resources in order to survive. It was kind of like survival of the fittest in a sense, in terms of humans and in terms of countries and nations. And Darwin, all he really did was kind of take Malthus's theories and just apply it to the natural world, right? So Darwin saw that plants and animals reproduce much faster than humans, right? If you look at an oak tree in your backyard, there are thousands of acorns that one oak tree drops. You're not going to have thousands of extra oak trees in the next season, right? Most of them are, almost all of them are going to start to germinate. Same with kind of frogs, right? Here, look at this one frog. Look at all the eggs that this one frog has laid, right? Not all of those tadpoles are going to survive. Right. So if nothing were limiting reproduction, plants and animals would overrun the earth. Obviously, they don't. So this means that the majority of organisms, right, that reproduce, the majority of their offspring are not going to survive. And we've already kind of spoke about that concept. Okay. And which ones are going to survive? Well, the offspring that are the fittest, that have a slightly different trait that makes them more fit to survive and reproduce. Okay, so with all this, right, Darwin kind of eventually got to the point of, all right, I have my theories written. He had his book written, all right, on the origin of species, right, 1859. This is 30 years after he sailed in the Beagle. The book's ready to go, but he still wasn't ready to publish it. And it was really kind of what pushed him over the edge with this other scientist named Alfred Russel Wallace, who wrote a letter to Darwin, like kind of like stating some of his theories to Darwin. And Darwin realized that this guy, Alfred Wallace, was like right on track, almost identical to Darwin's ideas. And at that point, Darwin was definitely had more information written down. It definitely had a more robust theory, even though they mirrored each other. Darwin realized if I don't publish now, the first one to publish is the one that gets credit. And that's when Darwin finally like, okay, 1859, puts out his book. Now, each living species is a result of millions of years of evolution. We kind of know this, right? This is his theories of natural selection. Darwin's ideas have shown to be accurate, while others have been disproved, right? However, the body of knowledge built on the concept of evolution is always changing. And all that is this, is Darwin kind of introduced the framework of natural selection. But obviously, the information we have today compared to what he had back then, like, he didn't really have an understanding of genes or genetics or anything like that. So Darwin's fundamental theories were all correct. We've just kind of have improved them over time and shifted some details over time, right? But the main theory of survival of the fittest, natural selection, organisms change over time, that is fundamentally correct. And that was a very, very big idea coming from Darwin. Okay. Now, what we know with this is, right, this process of natural selection, it doesn't really turn on, turn off. Like we spoke about punctuated equilibrium and gradualism, right? But that's really kind of the rates of natural selection, right? Whether it happens fast over short periods of time or slowly over long periods of time. And we know that kind of it depends on the organism, depends on the environments. But there is this constant change, right? The environments are constantly changing. Our world is a dynamic world, right? It's always changing and fluctuating. It's not a static world. And with that, right, the health of a species or the ability of a species to adapt to its environment is really a key way to kind of measure the health of that species. And where does the ability to adapt to the environment, where does it come from? It comes from variation, right? So organisms that have a lot of variation, or species that have a lot of variation in their species, right, have the ability, because they have different genetic makeup, have the ability, if the environment shifts, there's a good chance that some of those offspring are going to be able to survive, right? So if enough variation exists in the species and environmental conditions change, the species will evolve, right? So if there's enough variation in the species, if there's a change in the environment, there's a good chance there's some variations in those species that will make the new organisms or the next generation fit for the new environment. Okay, so 2 examples I'm going to go through with this. We give you a lot of examples in this chapter, but one is the peppered moth, which is back in England in the 1760s. We're going to do an experiment with that next class. And the other one is kind of antibiotic-resistant bacteria. So those are the 2 examples, which I'm going to go to the next slide to give you some images. So here's a peppered moth. The one on the bottom is kind of like the initial coloration of peppered moths in England in the late 1700s. Okay, now late 1700s, there becomes more coal production, more coal being burned, right? All these factories in England, right, putting out all this soot, and a lot of trees, and a lot of houses, and a lot of areas started becoming with like this dirty black soot material. So what they noticed over time is the peppered moth started to kind of change its color. This is the baseline peppered moth color. However, if I have a dark kind of smog coating, dust coating on the trees or on the surface of a house, right, this moth is going to stand out very, very bright, and it's going to be very easy to see for predators. So over time, the lighter coloration was selected against, but there was variation in their species. Some of the peppered moths had slightly darker coloration, and the ones with slightly darker coloration were the ones that blended in better to the background. So over time, your peppered moth population changed or shifted from the lighter color to the darker color. It doesn't mean there weren't any more light ones. It doesn't mean that they were all the dark color, but the frequency of the dark coloration compared to light coloration started to go up. And if you think of alleles dictate the color. Right, so the alleles that dictate the darker color, those allele frequencies, percentages are going up. The alleles that dictate the lighter color, those allele frequencies are going down. Okay. Now the other one was antibiotic-resistant bacteria. So with bacteria, there's a lot of variation in bacteria as well. Even though they reproduce asexually, there's a lot of mutations. They can get a lot of variation there as well. Not quite as much as sexual reproduction, but it does happen with asexual reproduction of bacteria. So when you treat something with with antibiotics really attack the cell walls of the bacteria and destroy the bacteria that way. However, there are some bacteria that have genetic makeup that make them resistant to the antibiotic drugs. Okay, so when you treat, let's say you treat like a cow, right? You have a cow that's sick or a cow that's you're trying to keep healthy, you're treating with antibiotics, or even a human, right? You might take those antibiotics, it might kill out most of the bacteria, but there might be a couple variants there that have some resistance to the drug. Okay, so the antibiotic works, however, some bacteria survive, and the ones that survived were the ones that had some resistance to the antibiotics. So therefore, those bacteria, because they survived, are going to start reproducing. And then if you were to kind of use that same antibiotic again, it might not work as well because there's going to be a greater number of bacteria there that are resistant to that antibiotic. Okay. So 2 last things, the importance of genetic diversity, we kind of keep highlighting this, right? Variation is key, right? Genetic diversity gives rise to inheritable variation, providing raw material for evolution, right? The more variation there is in a species, the more possible different adaptations there are. If the environment changes, the species can shift along with it. Without genetic diversity, natural selection would have nothing to act upon, and species would not change. So if all organisms were the same, there'd be no real winners, no real losers. If everybody's equal, right, therefore there's going to be no natural selection. It'll just be randomness of shifting in all different directions all at the same time, right? So that variation is key. Species must be able to change because of natural processes and human influence. Genetic diversity is a result of millions of years of random mutations, natural selection, and genetic drift. Okay, so what is this first one saying? Species must be able to change because of natural processes, right? The environment's constantly changing. It's naturally changing. Human influences in terms of habitat loss and climate change, and we are impacting the environments dramatically, and the species that have variation that can adapt to that are the ones that are going to survive, right? And then the genetic diversity in this world, where does it come from? It comes from just random mutations that take place. It comes from natural selection. It comes from genetic drift as well. So genetic drift is just a randomness and changes. So just realize that diversity in this world is really coming from two main sources, which is going to be mutations, all right, and then kind of that genetic recombination, right, that meiosis process. One quick thing there is actually a little bit kind of wrong, which I'll say to you why. My question to you would be, what does natural selection do? Does natural selection itself increase or decrease genetic diversity? I'll give you a moment to think about it. So does natural selection increase or decrease genetic diversity? All right. How many people said increase? How many people said decrease? All right. Natural selection itself actually decreases genetic diversity, right? The variation doesn't come from the actual natural selection part. Just think about it. Natural selection is choosing one winner, and then there are losers. So natural selection, by choosing, like, let's say the peppered moth, it's choosing the darker colored moth, it's decreasing the numbers of the light colored moth. So the actual selection process of natural selection decreases variation. However, we need variation for natural selection to play. So where does the variation come from? It comes from random mutations. It comes from genetic recombination, meiosis, right? That randomness in reproduction is what increases the variation, although natural selection itself actually decreases variation. If you have any questions, we'll talk about this in class. Hope you kind of understood. And if you're kind of looking through, just go ahead and fire off questions when we get to class today. Thank you very much.